Hello, Gordon.
Hi.
Hi.
You too.
Nice to see you again. How are you?
Very well, thank you.
So I think one of the things that I'm trying to do, especially after I finish, is try to complete this book I've been writing for the past few years. I'm just like really dedicate some time to completing it. And it is a leadership book. It's kind of, the title hasn't been finalized, but it's something around leading self, leading others, leading change. And it's, there's the foundations, obviously. And in fact, I was writing a portion of the foundation section of the book this morning, which is very much around the history of the universe and where we came from and evolution and things like that, because I think we need to kind of remind people.
So you're grounding this book in a very deep and extensive way.
Yeah, absolutely. Even though it's a lot of it, obviously it's around the human factors and leadership. I think it's very important to remind. It's aimed at students, and it essentially what it will become a textbook, hopefully, for the subject I've been teaching for a number of years, and the leadership. So it's been about a decade now. I've been teaching in the space of leadership and human factors. So it's very much, bringing everything together in a very cohesive, coherent manner, but also really highlighting some of the things I really emphasize on is like, which has some scientific but also philosophical components. So I was writing the section which was from the Big Bang. How 13.8 billion years ago, that's when it all happened, and stars and galaxies formed and planets, and as the universe cooled down, atoms were formed, and heavier atoms after hydrogen. So all of those things, but it's just I think it's really important to highlight that even in a book like this, you don't find something like this in a typical leadership book, because people just take all of this for granted, and I think it's not. I don't think we should take what we know scientifically for granted. A leader needs to know these things, or at least be reminded of them, because some people even know, but they forget. Essentially, and I'm kind of trying to just provide the facts, or at least what we know. And all of this obviously changes, but this is what we know thus far, and then have some reflective kind of activities after each section, after each chapter, saying, okay, what are the implications? So here's the Big Bang. What does that mean for you in terms of leading yourself, leading your relationships, leading change, and leaving it for the students to kind of be creative and reflect on what that actually means for leadership. And that's what I'm curious about. So my successor will hopefully have a kind of I guess first edition of this textbook for when she teaches in August. So I have about between now and August to kind of put something together.
Well, now this all raises a question for me. What's your impression about the what do I want to say, the breadth or the frequency of people at other universities who do what you do here at Sydney? Do most universities have people who teach leadership primarily to engineers?
No, I think, well, there is yes and no, because I know there are programs out there. There's like engineering leadership programs at other universities, including Penn State, but also in Melbourne. I know there's and in Queensland. So these are different states in Australia, which I know there are programs that do have some elements of leadership development. Now, I think everyone has a different approach to it, because it's such a broad and theme, and there's so many angles you can tackle leadership, and that's
Right.
you ask 5 leadership experts what leadership is and what it's about, and they will give you 5 different answers, right?
Right. Yes.
And these days, the focus is very much around, servant leadership, emotional intelligence, so leader as a servant, and so it's transformational leadership. So there are a lot of theories out there around leadership, but nothing really tackles the deeper issues of where we came from and why do we even need to have emotional intelligence, right? Like what is the foundation of empathy in terms of can we make sense of it by looking at more deeper fundamental questions or theories and knowledge that we have from science and philosophy? And that's kind of where I want to kind of close that gap, instead of saying empathy is a good idea, but just giving some kind of more like a deeper framework than what just kind of opinion about some of these theories. Of course, some of them are well established, but so that's and I'm hoping this textbook would obviously, it may sound ambitious, but if it's successful, hopefully it can be also used by other programs and institutions. And I know it's not. It's probably something that will evolve over time, because I think this is.
How do you plan to publish it? What's your mode of publication going to be?
That's one of the questions that I've been kind of grappling with, like whether I need to find a publisher, and ideally a publisher, like a well-established publisher, where I can have that, someone take that on and publish it. Obviously, there's also self-publishing, but I don't know if that's the good thing with self-publishing is you can keep updating it without having to go through all that bureaucratic processes, and it's just like, okay, I just need to update this now, and you just do it, uploaded the new transcript on Amazon, and that's it.
Yeah, the difficulty with opportunities like that is that they become obligations.
Yeah, like in terms of even self-publishing.
No, I'm thinking of updating. I mean, yes, you can update, but then it starts to feel like an obligation. You must update with a certain frequency.
Yeah, I mean, I think I have a it's all about really just time management as well. Like, I think I want to have the most accurate, most up-to-date version of like what I want to say, and I know it's the first edition or the first version is just not going to be perfect, but I just need to get it out there, because otherwise, if it's not out there, it cannot be critiqued, it cannot be I think that's it's when it's out there, it's public, people can read and critique it and find flaws, find issues, and I know they will. I it's almost like it's not a matter of if, it's a matter of like where and when, and and how much, right? And so that's, I'm certainly prepared for that. And I think that's the evolutionary path of the book, is that it will be revised and refined over time. But I just need to get. I think it's kind of, I'm battling with this because I've been trying to write this for the past 5 years, and it's just like. And I compiled everything I've written. It's about 1,500 pages. It's not for one book, obviously, but it's like, it consists of poetry and stories and
Is there a chapter or a section on consciousness?
Oh, absolutely, there is. So I'd love to get a chance to send it to you and to have a read, and and especially the parts which we've been talking about around consciousness and all the stuff that we've been discussing,
Right.
yeah. So that's the plan, and I guess very much like the approach with I think education in general, and this book will kind of reflect that, is very much, here are some facts or even theories and ideas. What does that mean for you? And that's like really asking students and the audience or the reader to really kind of sit back and just reflect. And essentially, in this subject, what I'd like is that kind of debate, discussion around that. So students may read a chapter, watch a video, whatever it is, online on Canvas, which is the learning management system we use, or in the book, and then have some discussion around it, and what are the implications of this. And so that's the kind of approach that we have, and I'm very much pro experiential learning, so it's very much also creating some kind of activities where they can do that activity and just have some reflection and discussion around it. So that's be a lot of that in there.
Yeah.
So one thing that I had actually a few ideas last week, and I should have written them down, but it's kind of like I think I've forgotten some of them. But
I know what you mean. Yes. Fleeting thoughts.
But I guess since I was just writing a little bit about the Big Bang and singularity, maybe if it's okay, we can talk a little bit about that, and
Sure.
we've touched about that on that, and we talked about the Big Bang, the singularity, and the Big Bounce, and kind of that idea of expansion and contraction. And one of the things that fascinates me is that the idea. I mean, if I guess what I'd like to talk about is the singularity itself. It's at we know that it was a point of infinite mass and infinite gravity when that happened. But
it's a little strong to say we know that.
Oh, yeah.
What we think is reasonable is to take the expansion that we observe and try to model it reasonably well in the context of general relativity theory. And then, assuming that our model is adequate, we reverse it and run it backwards in time to the distant past, where, if the evidence continues into the distant past, of the kind of evidence we have now, then it's plausible that the universe just becomes hotter and hotter and more dense, more and more concentrated. And if that continues indefinitely using general relativity, then roughly 14 billion years ago, everything is condensed into this singularity. But it goes a little far to say we know that that's what's going to happen. We don't know that. It's a plausible, possible consequence of the data that we have. Most theorists working today trying to improve our theories for the distant past are in one way or another, I would say, working to undermine the whole idea of the actual existence of the singularity 14 billion years ago. In many cases, you would replace it by a big bounce conception, in which there's an upper limit to how hot the universe gets or how dense the energy concentrations in the universe become. An upper limit which, when reached, then kind of reverses, and the universe goes into a kind of reverse expansion, reverse in time, but if time is flowing in our natural direction, that becomes a contraction to the big bounce and then an expansion following that. So if those ideas, and there are many different forms of ideas like that, if those ideas pan out in the sense that we eventually get supportive empirical data to support them, then the singularity is something that never quite happens, because the universe does not contract in the distant past to the singularity. It contracts to a maximum level of contraction and then reverses. And that is where I see almost all of the theoretical effort that's going on in early days cosmology these days, is to somehow, I won't go so far as to say it's motivated by the desire to get rid of the singularity, but that just seems to be the natural consequence of the way most theorists are thinking these days.
And I find that very, I mean, for me, naturally, I'm inclined to feel that the big bounce makes a lot of sense.
Right.
So it's, and what you mentioned about, you know, the expansion. So let's say, for instance, where we are right now, the universe is still expanding. At some point, it will start slowing down, and it will start kind of reversing, or, you know, everything starts kind of contracting again. So that, from what I understand,
that's a possibility. That's a possibility, but the evidence we have right now indicates that the expansion that's going on right now is actually accelerating. And it's a question whether in the distant future that will ever reverse, and it'll start decelerating and maybe eventually turn around into a contraction. But if the theoretical model that people are using right now, with a simple cosmological constant added to general relativity, if that's the whole story, then there won't be any decelerating period. It'll just keep accelerating, and the expansion will keep getting faster and faster and faster, with rather disastrous consequences for anybody who happens to be around sufficiently long into the future, because everybody gets pulled apart, everything gets pulled apart, and eventually even the atoms comprising everything gets pulled apart. But that's probably a simplistic model. I mean, it would be unbelievably remarkable to me for the simple model that we're using now to continue to work arbitrarily far into the future. But if it does, then that just means the expansion is going to get faster and faster as time goes on.
Are you
Yes, I see it.
Excellent. Okay, all right. So hopefully we can work on this.
This is wonderful. I've never seen this done before.
No, this is the first time I'm doing this, so that's great. So let's consider the bouncing universe.
Okay.
Something like that.
Right.
I'll correct it at some point. But what we are looking at is, let's say if we take T1 here.
Yes, that would be a good choice. That would give us our presently accelerating expansion. But since we're dealing with a bouncing universe, in that model, eventually the accelerating expansion will turn into a decelerating expansion, go over the top, and then come back down, contraction, and enter the bounce. And there's a period between where you have T2 and go to the left and put in a T0 symmetrically on the other side of the bounce. Okay, put the T0 where you were going to put it, right at the bottom, right at the lowest point.
Okay, yep. So here basically.
Yeah, that's T0. Okay. So that's the very center of the bounce. That's the point of maximum temperature, maximum energy density as we work our way back.
Mm-hmm.
But now imagine a T minus 1 or a T minus 2.
Uh-huh.
Put one or another of those in the diagram.
So before that, something like this?
Yeah. Very good. Yeah. Now, the interval from T minus 1 to T2,
Uh-huh.
that's an interval during which the velocity is accelerating. The velocity of the expansion is negative at T minus 1. And
Correct.
so
Yeah.
we say that the universe is contracting, not expanding. But you could say that it's expanding with negative velocity, which means it's really contracting. But that negative velocity is gradually changing into zero velocity at T0, and then into positive velocity at T1, and even more positive velocity at T2. So you've got an acceleration of the velocity from a negative value at T minus 1 to a maximum positive value at T2. And then after T2, the acceleration of the expansion essentially stops and starts to pick up a deceleration as you go over the hump,
Exactly.
over the top.
Oh, goodness. This PowerPoint is not as nice as I had them on. I'm starting to move everything as I try to draw new things. So that's V2, which is higher velocity. And then, but when we continue, so that's kind of expanding. And then let's say if we have a...
yeah, that's pretty much the fastest velocity. Yeah, if you put that at T3, and the velocity at T3 is going to be a little bit less than V2.
Correct.
V3 will be slightly less than V2. Yeah.
Yeah, so V3 is less than V2.
Right.
And V2
V2 is greater than V1.
V2 is greater than V1, yeah.
And so it goes, V1 is greater than V0, and V0 is greater than V minus 1, because V minus 1 is essentially negative.
See if I can play around with the... And V1 is greater than V0, is that correct?
Yeah.
Yeah. Okay, so now, this is... So I guess this kind of... This graph is a more accurate representation if we consider T1 as, let's say, 2020, or 221.
Yeah. Now, the thing is, there are probably, I can't be sure of this right now. I don't really know the situation well enough to be sure, but I would guess that there are some theorists that are conjecturing or working with models in which you really have a situation as you've described it. You go through a bounce, you expand to a maximum, then the expansion turns around into a contraction, you go through another bounce and expand again, maximum, contract again, so on and so forth. So repeating over and over again. But I know that there are several prominent theorists like Julian Barber, Roger Penrose, and other people who have just one bounce. And while they have a contraction before that bounce and an expansion after that bounce, nothing ever turns around again. It's just a contraction from the eternal past, one bounce, and then an expansion into the eternal future, which never turns around.
So I'll create another slide, and we can maybe draw that as well.
Okay.
So in this case, what you mentioned here is that it's something like this, essentially. Is that right?
Yes, and the left-hand part just goes up and up and up endlessly, and the right-hand part just goes up and up and up endlessly, and there's only one bounce right in the middle.
And so where would we be at this time, like in 2021?
We would be, I guess I can't, put in a T0 right at the bounce. Now put in a T1 a little bit to the right. And a T2 just a little bit further on the right. Yeah, we could be at T1.
So that could be 2021.
Right. But T2 looks pretty, what I'm going to say, flat. It doesn't look like it's still accelerating. It's still expanding, and it'll expand infinitely, indefinitely, but it doesn't look to me like it's accelerating the expansion anymore. But at T1, there's still some acceleration of the expansion going on. So we could be at T1. So the time interval from T0 to T1 would be roughly 14 billion years.
Oh, I see. I got it. So that's this time here is
so yeah, roughly 14 billion years. Right.
And so let's say if we have T3 here,
right?
So does that theory say that the velocity at T2 is the same as the velocity at T3?
This would depend upon the details of just whose theory you're dealing with.
Uh-huh.
And in the case of someone like Julian Barber, I honestly don't know the answer to the question. It might be yes, it might be no. If it's no, then that probably means that there's still a little bit of acceleration going on, but it's extremely tiny acceleration.
Uh-huh.
Or it could even mean that the expansion is slowing down, but it's never going to go over a hump. It's just going to slow down and slow down and slow down and slow down, but never go over a hump.
I guess my question is, what is the logic behind this kind of graph in opposed to the one we just drew earlier, like this one? Like what kind of makes the theories not, for instance, not agree with this one? And I guess what the reason I asked that is this makes more intuitive sense. I mean, intuition probably is not the best kind of.
Well, the thing is, this graph you're looking at right now, the first graph you drew with the peaks and the bounce and the peaks and the bounce, that's a very old model that was popular for a while and can be found described in an old book on not quantum cosmology at all, but just general cosmology. And again, I'm blocking on the name of the author. He was a very well-known theoretical physicist of his day and a cosmologist. But people don't see any evidence for that kind of thing. Not to mention the fact that it would be extremely hard to gather any evidence either for or against it.
Mm-hmm.
But I know that Julian Barber thinks he has good theoretical reasons for believing in a single bounce universe that contracts endlessly from past eternity to a single bounce and then expands endlessly into the future. But he doesn't have strong empirical data to support that. He just has theoretical reasons which appeal to him.
Right.
Roger Penrose has another description. I wish I could do a PowerPoint, but I can't. But you can watch my fingers. In Roger Penrose's scheme, there is like expansion from a minimum, and then the disappearance of time, and then another expansion from a minimum, and then the disappearance of time, and then another expansion from a minimum, and then the disappearance of time. It's very similar to a bounce maximum, except the connecting link between the bounces and the maximums are somehow dissolved. And it's very hard to get a grasp on what's going on. It's essentially his claim that when the universe has expanded sufficiently, then all mass disappears and all the quantons move with the speed of light, just like photons do. And once that happens, there is no longer any time, because time depends for Penrose, crucially, on the fact that the quantum frequencies associated with various quantons depend upon their differences in mass. If they're all photons, if everything's moving at the speed of light, then the whole idea of the passage of time and velocity and even moving really loses its meaning.
Yeah.
So what happens once that occurs, and its occurrence is a very gradual thing, but what happens once that occurs is that some statistical fluctuation starts the whole process off again, not from a singularity and not from a bounce, really. It's just the expansion process starts from the beginning again, as if it were a beginning. But he calls it a cyclic universe. So it goes this way, and then this way, and then this way, and then without there being any maximum or any bounce.
Got it.
It's hard to describe, actually.
I'm going to attempt to draw that now, Gordon, if that's okay.
Okay.
From my understanding, please correct me if I make a mistake, but from what I understood.
If you look on YouTube, you can actually find him lecturing on this.
Yeah. Well, I mean, what I gathered in terms of the what he might look like is something like, if I'm still getting adjusted to this idea of drawing in PowerPoint. So something like this, is that right?
Yeah, right, yes.
And so it's like, time disappears in these gaps.
That's right.
So it's kind of, there's nothing there.
Well, no. There's lots there, but it isn't time. Time isn't there.
Time isn't there.
Space is there.
So
no time.
Over here we have just like photons only, basically.
Yes.
Only region, basically, and photons are traveling at the speed of light, and if you're traveling at the speed of light, time stops.
And what we're saying photons only because everything that's there is traveling at the speed of light.
Correct.
So they might be really electrons, they might be quarks, they might be neutrinos, but they're all traveling at the speed of light, so they're all like photons in that respect.
Got it. That's really interesting. It's intriguing, and I think it does make sense to have that, like in terms of everything's traveling at the speed of light, time stops, because if you travel at the speed of light, there's no time, which makes sense.
He calls this the cyclic universe.
What's the name?
The cyclic universe theory.
And how do we spell that?
C-Y-C-L-I. No, C-Y-C-K-L-I-C. I think I've got a book with the name, with the title. Just oh no, the title of the book is Cycles of Time. That's his book about this particular model, Cycles of Time.
And this is Penrose.
Yeah.
Yeah. Interesting. I mean, I favor this one, but obviously, whichever has the biggest.
Well, I'll tell you what, downstairs I have the book that has this bouncing universe, multiply bouncing universe. After we're done here, I'll go down and get it, and I'll text you the title of the author's name and the title of the book, stuff like that.
Oh, thank you. Thanks, Gordon. So these are essentially the three theories or most established models that exist.
Well, right? let's be careful. None of these models are established, except you could say they're established as models. Yeah. But they're certainly not established as correct theories.
Got it.
They are models looking for evidence.
So it's yeah, got that. The reason I mean, this might sound very naive. The reason I still favor this one is because everything in nature has cycles, and from breathing to the heart rate to cycles of day and light, everything has a cycle, and a sinusoidal cycle, in fact. And so if nature is somehow reflecting the nature of the universe itself and how it came to be and how it will
right.
go out of it, it just makes sense intuitively that's kind of the way it is. So I'm also looking at nature itself, and that's why.
Yeah, and I have to say that while maybe the specialist cosmologist would disagree with me, from my perspective, if you put us in at time T1 or T2 in this bouncing universe, cyclic bouncing universe, I don't think we're in possession of any evidence to rule out that possibility. It's got to be regarded as still a possibility.
But in terms of this graph, we definitely would be somewhere in T1 because of
that's right.
We know for a fact that the velocity of expansion is increasing, so we must be there,
yes,
right?
That's right. And what we don't know is how long that will continue, or whether it will stop and turn around at the peak that you've drawn. We just don't know that.
I guess the challenge would be to somehow measure the speed of expansion as far as if you let's say we consider a few million years ago, and how the rate, the speed of expansion then, and then how it is now, and then perhaps how it will be at some point in the future, but it will still not be enough because we just don't know how far.
That's right. And the thing is, it's one thing to get evidence from the past and see how things were happening then, and compare them with what is happening now. And that tells us that the expansion is accelerating. It's very hard to get evidence from the future. Very hard indeed, because signals don't come to us from the future. They come to us from the past.
Yes. At some point, there might be some technology that might help us with that, but I don't think we're anywhere close to.
Right.
But no, fascinating. Thank you so much for that.
You're quite welcome. It was enjoyable.
Okay. Well, thank you so much, Gordon. I'll look forward to see you in 2 weeks' time then.
Okay. Very good.
Thank you so much. Have a lovely day. Have a lovely night, Gordon.
Okay. You too. Bye-bye.
Good night. Bye-bye.